Hi everyone. Today, the topic is going to be about graph traversals. Graphs are a key topic when it comes to advanced data structures. Let's dive right deep into it. So, let's talk about graph traversals. Graph traversal algorithms explore nodes and edges in a graph. There are two fundamental algorithms when you want to traverse nodes in a graph. The first one is called breadth first search, and the second is depth first search. I'll be talking about each of this in detail. Breadth first search. I'm going to be using the abbreviation of BFS across the lecture. BFS explores the graph level by level, and it starts from the chosen source node and visits all of the neighbors before it moves to the next level. The key characteristics with BFS is while storing, it uses a queue data structure. It follows the order of FIFO. FIFO stands for first in, first out. Also, when you traverse a graph with BFS, you're guaranteed to have the shortest path in an unweighted graph. So if you ever have a question of directly finding the shortest path and the given graph is an unweighted graph, go for BFS. Two key applications of BFS. The first is the shortest path finding. Whenever you have to find the shortest path, in case of an unweighted graph, BFS is the way to go. Also, when you have to have social network analysis, because BFS first goes to all of its neighbor before increasing in its level, it is very much applicable for any kind of a social network analysis wherein each node has to be first associated with the neighboring nodes than the depth nodes. Let's look at how the BFS algorithm works. There are two key steps. The first one is to enqueue the starting node and mark it as visited. And the data structure we are storing it is in a queue format. So the loop for the algorithm is while the queue is not empty, you dequeue a node, and for each of the unvisited adjacent node to it, you mark it as visited and enqueue the node. And you do this while your queue is not empty. This will ensure you get a BFS path outside. Before we dive into the code part of it, let me show you what BFS actually looks like. So now, let me draw the graph that I'm trying to find. This is for BFS. So I have 7 nodes effectively. Let's number them. 3, 4, 5, 6, and 7. And let's keep it simple. This is what the graph is like. Now, whenever we're traversing BFS, this is our source node. Now, from the source node, you have to visit the neighbors first. So the way your path is going to look like, let me use a different color for the path. First, you go here. So if we look at the BFS traversal, so I visited the source node first. Now I went to 1. Now I have to find the neighbor of the source node. The next neighbor is 2. So basically, you're traversing the next neighbor. Once you've reached 2, then you go to 3. That's the next neighbor. Does my source node 0 have any other neighbors? No. So then I now am here and I'm finding the neighbor of the node numbered 1. That is 4. The next neighbor is 5. There are no more neighbors to 1. That is when I'm here on node number 2. And there's only one neighbor, 6. After this, I move here. Here with 3, my neighbor is 7. So my output, the BFS traversal, is now 0, 1, 2, 3, 4, 5, 6, and 7. If you see here, we first started from our source node, traversed all of the neighbors in sequence. Then for each of them, I traversed the neighbors. This is how BFS works. Now that we have Now that we have seen the algorithm in action as well, let's look at how would BFS look like in code. Taking the example of Python, you can use TQ, and this is the code for BFS. If you see, I'm marking the node to be visited, and then I'm adding my start node or my source node. And while queue is not empty, I keep on appending, visiting the nodes and removing them back. You can refer this in order to solve questions. The next topic is depth first search. Depth first search is another graph traversal algorithm. So let's look into it. Depth first search explores as far as possible down each of the branches that's there before it backtracks. So if I have to consider everything, let's see what do the characteristics of DFS looks like. It uses stack as a data structure. It works in the form of LIFO, last in, first out, which is also synonymous to the recursive function call. In this, you can go deep quickly and explore paths until completion. Two key applications are if there's a pathfinding in puzzles, wherein you have to go in depth of one section before you move on to the next. Also, in topological sorting, DFS is used. To look at the algorithm, the first is that you start at the chosen node, which is your source node, and mark it as visited. And you recursively visit each unvisited adjacent node and then backtrack when there are no unvisited nodes remaining in your path. There's also an alternative approach of an iterative approach wherein you use a stack instead of recursion. We'll be looking at both of those code forms, but before we dive into the code part of it, let's actually go ahead and look at what DFS looks like in action. So now let's look at what DFS looks like in action. Let's consider the same graph we considered for that we considered for BFS for DFS. So this is DFS. My graph had 7 nodes. Let me quickly draw the nodes. I'll number them 0, 1, 2, 3, 4, 5, 6, 7. These are the connections for my graph. I'm keeping it same so that you can understand the difference between BFS and DFS. Now, let's look at what the DFS traversal looks like. I'll use a different color in order to show you how it looks like. Here, this is my source node. So first, my visited node is 0. Now, I visit 1. Now, after 1, this is DFS, so we have to go in depth first. So instead of looking at the neighbor, I'm first going to see if there is something that I can go in for depth or not. And I see that there is an adjacent node which is unvisited that I want to visit. So I go here and I select 4. So the next visited is 4. I then come back. Then now, is there any other unvisited? Yes. So that is 5. I come back up. Now there's nothing else left to be visited from 1. That is wherein I now proceed to 2, which is, so I come back and then now I'm visiting 2. After 2, I see that there's 6. So 6, I come back to the source node, see the next one, 3. Again, see 7. There's nothing here, there's nothing here, and we are all done. So now we have our result as 0, 1, 4, 5, 2, 6, 3, 7. So this is my DFS traversal. Now let's look at how this looks like in code. So this is the direct approach for the code, wherein I'm using a recursive way of looking at each of the nodes, visiting them, and moving ahead. The second one is the iterative way that I can use with the use of stack, making use of LIFO, last in, first out, and then marking everything as visited and then removing things and going about everything. Now that we had Now that we have looked at both BFS and DFS, let's look at a few comparisons. So in case of BFS, the data structure used is queue, which follows the order of first in, first out. In case of DFS, it is either stack, which follows last in, first out, or recursion. The pathfinding optimality is there in BFS, especially, or the pathfinding optimality is there in BFS when using unweighted graphs, whereas in DFS, it is not guaranteed. The memory usage is more in case of BFS because of the use of the data structure of queue. In DFS, it is less because there are recursive calls. The traversal type is level-wise in case of BFS, whereas in DFS, you go depth first. It is depth-wise search. Now, let's look at the conclusion and the key takeaways. BFS explores a level by level and DFS goes in depth down each path. Both are fundamental for problem solving in various computational fields. Now, how do you choose BFS or DFS for each of the different things? You will use BFS for level-based searches and DFS for depth-based exploration. So that's the end of this lecture. See you in the next lesson.